In this lecture on fMRI data analysis, we'll be looking at a special case of the multiple linear regression called deconvolution. Let's say we have a person performing the task briefly at these 3 time points indicated by the arrows here. Now, one way to analyze that would be to convolve those times with the hemodynamic response function and then fit that to the data. However, what if we don't want to make any assumption about the particular shape of this ideal response? Rather, we just want to see, are there any significant changes that are time locked with my stimulus? And then what do these changes look like? The way we can measure that is with deconvolution. Now, if we have the signal as illustrated here, one way to do this would be simply to cut the time series at these different arrows, realign the data, and then average across those time points. However, what if the signal looks like this? We have a rapid event-related design. In this case, we can't just simply cut an average. So how can we obtain what the ideal response looks like that's time-locked with this particular stimulus? The way we can do this is by varying how we model the hemodynamic response. In the first row is what we should see with a fixed hemodynamic response function shape. We simply have a single function that we convolve with this timing in order to model our response. Instead, we can model this as a sum of different functions, in this case, these tent functions. So let me show you how this works. Let's say we have at the bottom here, these times at which we want to estimate the hemodynamic response function. What we would do is we'd create these tent functions at each of these times. And let's say this is what the hemodynamic response function looks like. So the way we can estimate that is by fitting each of these to the data. And then if we take the sum of all of these, it creates a piecewise linear approximation of the hemodynamic response. The benefit of this kind of way of estimating is that even if our data acquisition is not exactly synchronous with the times at which we want to estimate this hemodynamic response, we can still estimate this. And that is, for example, consider the data point right here, acquired at this point in time. We're modeling it with a sum of these 2 triangle functions. And the sum of these 2 triangle functions exactly provides us this particular line between the beta 2 and beta 3. So the way to think of this is that instead of having a single beta weight and a single response function that we're going to be convolving with our stimulus timing, we have multiples of these tent functions that together produce the hemodynamic response. The reason we call this deconvolution is because this process, convolving the stimulus timing with these functions and fitting it to the data, is what we call convolution, and rather going the opposite direction, that is, given the stimulus timing and our data, what does the hemodynamic response function look like, is called deconvolution. For a fixed hemodynamic response function shape, as you can see here, we would take the beta weight with a particular ideal regressor and fit that to the data. With these tent functions, we're essentially fitting some of these tent functions to the data. And if you look at the beta weights of these fits, they provide an estimate of the hemodynamic response function. So as you recall from before, if we have a fixed hemodynamic response function shape, we convolve that with our task timing. This is what the design matrix would look like. In the case of deconvolution, or with these tent functions, our design matrix would include more columns, one for each of these tents that we're trying to estimate.